Hello, lab. Hello, class. Whatever is relevant. What we're going to cover are the basics for determining empirical formulas, especially given our lab that dealt with oxidizing a metal and dehydrating a salt. For this first part, whether you do this part first or last doesn't matter, but what you're going to be doing is oxidizing magnesium. So you're going to be taking some initial magnesium and adding mass to it. Ideally, this this experiment is prone to error, so you might see that you actually lose mass. In which case, just assume that your mass of added oxygen is 0.01 grams if you're in one of my courses. But if things do go well, then for line 6, you should be able to get a positive change in mass by taking your recorded data from line 5 minus line 2. And then for line 7, take your data from line 3 multiplied by the reciprocal of the atomic weight of magnesium, 1 mole magnesium per 24.305 grams of magnesium. And then for line 8, that'll simply be your recorded value in line 6 multiplied by the reciprocal of the atomic mass of oxygen, 1 mole of oxygen per 16 grams of oxygen. Now, it's not described in the procedure, but the reason why your data sheet lists 2 different heatings is because you'll heat your sample once, then you'll let it cool, record the mass in line 4, then heat it up again for another 5 minutes, let it cool, and then record the mass. Ideally, the mass between line 4 and line 5 should not be different by any significant margin. That way, that indicates that all of the magnesium did in fact oxidize. Otherwise, if the mass does change significantly, heat it a third time and use that value instead of line 5 for your measurement of your mass of oxygen added. Now, we'll cover empirical formulas later. For part B, again, whether you do this part first or last, or you work with your group to do them both at the same time strategically, well, for part B, the main calculations are you're going to have a hydrated salt. That means some copper sulfate that has some water molecules around it. Well, for line 12, you'll get that answer by taking your recorded values from line 11 minus line 10. For line 15, the mass of copper sulfate, that will simply be your recorded value in line 14 minus line 10. Again, depending on if the value you get after your second heating isn't significantly different than your value after your first heating. If it is significantly different, then heat it a third time and use that value instead. For line 16, the mass of water driven off, that will simply be your recorded values in line 12 minus line 15. And then for the moles of copper sulfate, taking 1 copper plus 1 sulfur plus 4 oxygens, its molar mass will be 159.616 grams of copper sulfate per mole of copper sulfate. Simply take the reciprocal of that and multiply it by the value you record on line 15. That will give you moles of copper sulfate. Now, water, being 2 hydrogens and 1 oxygen, has a molar mass of 18.016 grams per mole. Take the reciprocal of that multiplied by your recorded value on line 16, and that will simply be what you put in for line 18. When it comes to reporting empirical formulas, the next few examples are going to be general cases. So essentially, for anything that is not a hydrated salt. Let's say after you do an experiment and you determine that you have a ratio of 1.15 moles of lithium for every 1.2 100 moles of fluorine. That's essentially taking your gram amounts and converting them to mole amounts. For empirical formulas, the next step that you do is divide every mole amount by the lowest number of those mole amounts. So in this case, that would be 1.15, and dividing both mole numbers by 1.15, that gets us for every 1 mole of lithium, we have about 1.05 moles of fluorine. And so essentially that's a 1-to-1 ratio, and you would write your empirical formula as LiF, or lithium fluoride. That's the general case. Another general case is, let's say we had 1.2056 moles of aluminum and then 1.8084 moles of oxygen. And then as we divide both numbers by the lowest of those numbers, we have 1 mole of aluminum for every 1.5 moles of oxygen. Well, if you ever have a simplified ratio where one of those numbers ends in 0.5, then there's actually an additional step. In that scenario, if one of your simplified mole amounts ends in 0.5, then multiply all of the mole amounts by 2. So that what we end up having is 1 mole of aluminum times 2 and 1.5 moles of oxygen times 2, getting us a ratio of 2 moles of aluminum for every 3 moles of oxygen. Therefore, now that we're at whole numbers now, the empirical formula would be Al2O3, or aluminum oxide. And that's just if your simplified ratio of mole amounts, if one of them ends in 0.5, whether it's 1.5, 2.5, 4.5, multiply the entire set of mole amounts by 2. Now, let's say another general case. Say after you had your gram amounts and you converted them to moles, we were left at 2.546 moles of iron per every 3.3946 moles of oxygen. Well, in that scenario, that will leave us with 1 mole of iron per every 1.3333 moles of oxygen. Now, in this scenario, where your simplified mole amounts, one of them ends in 0.33 or 0.3 repeats, essentially under that scenario, we have another additional step. But instead of multiplying by 2, we'll multiply by 3. And in doing so, what that gives us is a ratio of 3 moles of iron per 3.999, or rounded to 4 moles of oxygen. Therefore, the empirical formula in this scenario would be Fe3O4. And that additional step of multiplying by a factor of 3, that's a similar process if any of your simplified mole amounts ended with 0.66 or 0.6 repeats. So if you ever see any of your mole amounts end in 0.33 or 0.66, whether it's 1.33, 2.66, whatever, multiply all of your mole amounts by 3 to get your true empirical formula. Now, this case here, this is just relevant for hydrated salts. Hydrated salts, they have a very unique way of writing your empirical formula. So let's say we had nickel 2 sulfate and we had a hydrated version of nickel 2 sulfate. And by the end of our experiments, we realized we had, once we converted the gram amounts to moles, we had 3.4801 moles of nickel sulfate per every 20.8806 moles of water. Dividing by the lowest of those numbers, whether we had 2 mole amounts or 3 mole amounts or 4, it doesn't matter, dividing by the lowest number among our ratios, we end up getting, for every 1 mole of nickel sulfate, we end up having 6 moles of water. Now, instead of writing NiSO4 parenthesis H2O parenthesis subscript 6, do not do that for an empirical formula of a hydrated salt. For hydrated salts, it's a unique example. We're going to write the formula of our metal salts, in this case NiSO4, and then as if we're multiplying, write a little dot next to the metal salt formula, and then write the number of water molecules, the number of moles that you calculated for water, and then write the formula of water, so H2O. This would be the way to write an empirical formula for a hydrated salt. Therefore, for your actual experiments where you have copper sulfates, you're going to write copper sulfate dot the number of waters you calculate, then H2O. And that's what you should report for your empirical formula. Going forward to one of your additional questions in your data sheet, this is dealing with the mass percents of some compound. In this case, we're dealing with a compound that consists of 9 carbons, 8 hydrogens, and 4 oxygens. Well, a good way of measuring mass percents is take all of your amount, take the number of each element that you have and multiply by their atomic masses or their atomic weights as presented on the periodic table. In this case, we're dealing with a molecule that has 9 carbons, multiplying by the atomic mass of carbon, 12.01 grams per mole. That gets us 108.09 grams per mole. Taking those 8 units of hydrogen and multiplying it by 1.008 grams per mole, that gets us 8.064. And then taking 4 units of oxygen multiplied by 16 grams per mole, that gets us to 64. And just as a note, for myself personally, whenever I have the symbol of oxygen next to a number, I have a little bar over that O to signify that that is an oxygen and not, say, 40, but 4 oxygens. That's something I personally do. Your actual instructor might not have that, or you might have a way of writing your O's that's very clearly not a 0, but that's just how I distinguish, by writing a bar over oxygen whenever it's right next to a number. Once we add up all 3 of those weights, we end up getting a total molecular weight of 180.154 grams per mole. Now what we do is we take the amount of that 180 grams per mole that is just either carbon, just either hydrogen, or just either oxygen, and then divide those numbers by 180.154 and multiply by 100%. Therefore, 108.09 divided by 180.154 multiplied by 100% gets us an amount that is 60% by mass carbon. And if we take the amount that was just hydrogen, that would be 8.064 divided by 180.154 times 100%. That gets us 4.48% hydrogen by mass. And then 64 divided by 180.154 times 100%. That gets us to 35.52%. For these mass percents, I recommend rounding your answers to 2 decimal places when it comes to percentages, because oftentimes that results in mass percents that end up adding to 100, which is ideal. There is one additional step that I did not do, and I'm going to add right now. There you go. The last thing that I just added was identifying what those mass percents are. So 60% carbon or C, 4.48% hydrogen H, and 35.52% oxygen O. And yeah, that would be a way of solving this type of problem of mass percents. Just essentially taking the number of each element, multiplying by their individual atomic weights, adding up those those products that you get, and then taking a percentage of each relative to each element. For the last question on your data sheet, for para-dichlorobenzene, what we're going to do is figure out the empirical formula based off of elemental percent composition or mass percents. And for our problem, we're told that para-dichlorobenzene is 49.02% carbon, 2.74% hydrogen, and 48.24% chlorine. For any of you who take organic chemistry, you're eventually going to get to a point where you can look at the name para-dichlorobenzene and realize that there are going to be 6 carbons, 4 hydrogens, and 2 chlorines, and therefore an empirical formula of 3 carbons, 2 hydrogens, and 1 chlorine just from the name. But we're not there yet. For this problem, assume that you're working with a 100-gram sample. Therefore, 49.02% carbon just becomes 49.02 grams of carbon. And then if we multiply that amount by the reciprocal of the atomic mass of carbon, that gets us to 4.0816 moles of carbon. For these types of scenarios, I usually prefer to go to 4 decimal places for my mole amounts when I'm going to eventually calculate empirical formulas. But you could go further past that if you would prefer. Now, if we're told that we have 2.74% hydrogen, and we're assuming we're working with a 100-gram sample of para-dichlorobenzene, well then that means that 2.74 grams of that will be hydrogen. Converted to a mole amount, that will be 2.7183 moles of hydrogen. And lastly, 48.24% carbon, converted to a gram amount out of 100 grams, would be 48.24 grams of chlorine, multiplied by the inverse atomic weight of chlorine. That would be 1 mole of chlorine per 35.45 grams of chlorine. That gets us 1.3608 moles of chlorine. Now we can compare the mole amounts as a set of ratios. 4.0816 moles of carbon per 2.7183 moles of hydrogen per 1.3608 moles of chlorine. Dividing each of those 3 numbers by the lowest of those 3 numbers, 1.3608, that gets us, for every 3 moles of carbon, there are 2 moles of hydrogen and 1 mole of chlorine in our empirical formula. Therefore, we would write the empirical formula as C3H2Cl. Again, the empirical formula is not necessarily the structural formula for para-dichlorobenzene. The structural formula is C6H4Cl2, because that would be the actual number of each element in that molecule. But empirical formulas just tell us the lowest whole number ratios of each individual elements. Now, just as a reminder, if your mole amounts don't end in 0.33, zero point 0.5, or 0.66, then normally just round it either down or up to a whole number and then go from there. And if they don't, in any case, I hope this helps you understand this lesson, whether or not you received it before doing the experiments or received it afterwards. And of course, wish you all a very good post lab and peace.